welcome to the Screencast Modeling with Rational Functions. In section 5.3, we encountered a class of problems where a key quantity was modeled by a polynomial function. We found that if we considered a container such as a cylinder with fixed surface area, then the volume of the container could be written as a polynomial of a single variable. For instance, in activity 5.3.3, we considered a cylinder with surface area 60 square inches. We knew the constraint was surface area A, and that A equaled 60, which equals 2 pi r squared plus 2 pi r h. And we found that the volume could be modeled by V equals pi r squared h, which could be simplified to equal 30r minus pi r cubed by using the constraint equation. What happens if we instead fix or constrain the volume of the container and ask about how the surface area can be written as a function of a single variable? So suppose we want to construct a cylinder that holds 60 cubic inches of volume. How much material does it take to build the container using the minimum amount of materials? So our constraint is volume. Right? We're told volume, but also these units, cubic inches, are a huge indicator that we have volume. So 60 cubic inches, and we know with a cylinder, the volume, which is going to equal 60, equals pi r squared times h. The next step we usually do is isolate one of the variables in the constraint, and h would be easier since it's not squared. There's only a single h in that problem. So we would have 60 divided by pi r squared equals h. And we are trying to minimize the amount of materials. That means we are trying to minimize surface area. So we know the surface area of a cylinder, if it has a top and a bottom, so pi r squared would be the area of the bottom or the top. If we multiply that by 2, we have the area of the top and the bottom, plus the area of the sides is 2 pi r h. As it currently stands, the surface area is a function of two variables, r and h. But if we substitute this quantity in for h, then we can write this as a function of one variable. So the area would equal 2 pi r squared plus 2 pi r times the quantity 60 over pi r squared. And we can simplify that to equal 2 pi r squared plus 120 divided by r. And if we want a common denominator, I'll let you check that on your own, but it would be 2 pi r cubed plus 120 divided by r. So now we have the surface area of this cylinder, and it only depends on one variable, the variable r, the radius. So the question was, how much material does it take to build a container using the minimum amount of materials? And there's a few things we want to consider here. First would be the domain of the surface area function. Well, we know that because we have a rational function, the denominator cannot equal 0, so r cannot equal 0. But we also know in the physical context of the problem, it would not make sense for the radius to be negative. So our domain is going to be all positive real numbers, which means in this graph, we would essentially ignore this piece of the function. Okay. And if we want to minimize the amount of materials, we can look at this graph of surface area, and we see that there is actually a minimum point on that graph. So in order to minimize the amount of materials, the radius is approximately 2.122 inches, and the surface area, right? The amount of material is approximately 84.843 square inches. And so the question asked how much material. So ultimately, it's asking us for the surface area. And when you take calculus, you'll learn how to find these exact values. But for now, we can use the graph to find estimates.